So in this lecture, I wanted to go over some of the properties of matrix transpose and matrix inverse. And as usual, I'll not be proving all of these properties to you, but I would strongly recommend and urge that you actually consider examples or even prove these properties using the first principle. Alright, so the first one is pretty easy. So the transpose of sum of two matrices A plus B is equal to the sum of transposes of the individual matrices. This also is quite easy, right? The third one says that the transpose of a matrix is nothing but the matrix itself. The fourth one says that if A is invertible, so is A transpose. All right. And I think I didn't give you the conditions when a matrix is invertible. So the first condition, of course, has to be that the matrix has to be a square matrix for the matrix to be invertible. And the second condition is that the determinant of the matrix has to be not equal to 0. Because if the determinant of the matrix is equal to 0, the matrix is not invertible. And there is a little bit of terminology here. So non-invertible matrices are also known as singular matrices. So anytime whenever you come across the term singular matrix, it means that the matrix is non-invertible. It means that these two conditions hold true, or at least one of them. And right, so if A is invertible, so is A transpose, and you can check that in your examples, or you try proving it using the first principle. Then this condition will hold true. All right. The fifth one is that the product of the transpose of the product of A and B is equal to B transpose times A transpose. And you can see why this is not equal to A transpose B transpose, right? So just to give you an example, let's say if A is a 4/3 matrix and B is a 3/2 matrix, right? Then A transpose would be a 3/4 matrix and B transpose would be a 2/3 matrix. So clearly this multiplication itself is not justified, right? Whereas for the multiplication of B transpose into A transpose, so B transpose is a 2/3 matrix and A transpose is 3/4 matrix. So this multiplication is justified. Though of course this is not the proof that AB transpose is equal to B transpose into A transpose, but it does give us some hope in our belief that maybe this is true. And you can actually prove it by considering examples. The last one is quite similar to the fifth result, except that we are talking about inverses here. So AB inverse is equal to B inverse A inverse. And let me prove it to you. So let's say X be the inverse of, AB. All right. So what it essentially means is that ABX will be equal to I and X times AB will be equal to I, right? Now let's say X is equal to B inverse A inverse. Okay, let's substitute this. So AB times B inverse A inverse, this guy will be equal to, and now remember that the matrix multiplication, the process is associative, so I can combine B and B inverse terms here. So this gives me A into identity matrix into A inverse, and this further simplifies into A inverse, and this simplifies to I. So clearly it seems that ABX is equal to I when X is B inverse A inverse. All right. Now let's see the other case. Let's say B inverse A inverse times AB. Let's see what is this value if we substitute B inverse A inverse for X over here. Okay. Oops. So Again, collecting terms here, we can collect the middle two terms, A inverse and A, and this would give me I, B inverse IB, and this would be just B inverse B, and this would become I. So clearly, B inverse A inverse is the inverse of AB. All right. So I'll see you guys in the next lecture.